Today, we're going to crack open the most complex machine in the entire known universe, your brain. We're going to uncover the surprising science behind your best ideas, your deepest focus, and that incredible state we all chase called flow.
So, have you ever been there? You're staring at a blank page, nothing's happening, and then later you're in the shower and bam, the perfect idea just hits you. Well, you're not alone. It turns out that the very same part of your brain that lets your mind wander is also the secret sauce of your most creative breakthroughs. Let's figure out how that works.
All right, here's our roadmap. We'll start with a quick tour of your brain's basic hardware. Then, we're going to meet the two competing networks that are always fighting for your attention. After that, we'll discover the secret handshake that actually sparks creativity. And finally, we'll get into how you can hack this whole system for peak performance.
Okay, first things first. Before we get into the really cool stuff, we need to get grounded in the basics. You know, to really understand how your mind works, you got to know a little bit about the machine it's running on.
So what is the brain? Well, as Johns Hopkins Medicine puts it, it's basically our command center. We're talking about a super complex organ with something like 86 billion neurons, all firing away in these intricate patterns to coordinate, well, literally everything you do, think, and feel. It's the boss.
And the biggest part of this command center, the cerebrum, is kind of split up into specialized departments. You've got the frontal lobe, that's the CEO, handling all the big picture planning. Then there's the parietal lobe, your personal sensor, processing things like touch and taste. The occipital lobe is the visionary, turning everything your eyes see into actual images. And finally, the temporal lobe is like the company archivist, storing memories and dealing with sound.
Now this is where it gets really interesting, because inside this complex machine, there's a constant battle going on for your attention, a tug-of-war between two massive brain networks.
So let's meet your brain's two main personalities. On one side, you've got the dreamer. Scientists call it the default mode network, or DMN for short. This is your brain's screensaver mode. It's what kicks in when you're just spacing out or letting your mind wander. On the other side is the doer, the executive control network, or ECN. This is your brain's get-it-done mode, the CEO that takes charge when you need to really focus on a task.
And here's the crucial thing researchers have found. These two networks, they don't usually get along. They're basically on opposite ends of a seesaw. When your doer network is up and you're really concentrating on something, the dreamer is pushed down and suppressed. And the moment your mind starts to wander, that's the dreamer taking over, pushing the doer down. This is the real reason you literally can't daydream and write a complex email at the exact same time. One has to give.
And you can actually see this opposition happening. Using brain scans, scientists can track where the blood is flowing, and they can see the totally distinct territories of the dreamer and the doer. Just look at this. Notice how the active regions are almost completely different. They are two separate, competing systems vying for your attention.
So for a long time, we thought focus was all about making the doer stronger and just shutting the dreamer up. But it turns out the real magic, the secret to creativity, happens when these two rivals finally decide to cooperate.
When neuroscientists scanned people's brains while they were doing a creative thinking task, they saw something absolutely fascinating. It wasn't just one single area that lit up. Instead, this huge, distributed network of regions all across the brain fired up in perfect harmony, spanning multiple lobes and systems.
And this, right here, is the big reveal. Your most creative moments don't happen when the doer muscles the dreamer out of the way. Nope. They happen when those spontaneous, imaginative ideas from your dreamer network get passed over to the focused, goal-oriented doer network to be evaluated and refined. It's not a competition, it's a collaboration.
And this isn't just a nice idea. The hard data totally backs it up. Researchers found a direct link. People who have more efficient, stronger connections between their dreamer and their doer networks consistently score higher on creativity tests. It's all about that connection. So knowing all this, how can we actually encourage this creative cooperation in our own brains? How can we get them to work together? Okay, let's get into some practical, science-backed strategies to do exactly that. First off, let's bust a major myth: multitasking. Your brain can't actually do it. What feels like multitasking is really just rapid task switching, where you're forcing your doer network to toggle back and forth, back and forth. This is incredibly inefficient. Studies show it can slash your productivity by up to 40%, and it makes you way more likely to make mistakes. So what's the antidote? Single tasking. You can do this by designing a focus block. Just block off 90 to 120 minutes on your calendar. That matches your brain's natural focus cycle. Then, turn off every single possible distraction. Dedicate that entire time block to one and only one task. And when it's over, take a real break, step away. This gives your doer network the clear runway it needs to really perform.
And here's another hack that's a total non-negotiable: sleep. Seriously, think of it as nightly maintenance for your brain. It's when you lock in memories, clear out all the junk that builds up during the day, and recharge both your doer and your dreamer networks. Getting enough quality sleep literally strengthens the connections between them, making that creative teamwork we talked about much more likely to happen.
And this brings us to one of the most powerful and, honestly, most empowering ideas in all of neuroscience: neuroplasticity. The idea that your brain isn't fixed, it's not set in stone. Every single time you learn a new skill, or practice focusing, or challenge yourself creatively, you are physically rewiring its structure. You're building new connections.
So ultimately, you are the architect of your own mind. By understanding how the dreamer and the doer work together, you can intentionally build stronger, faster connections between them. You literally have the ability to train your brain for more focus, more flow, and more creativity. So the only question left is, what are you going to teach it to do next?
Welcome back to the Deep Dive. You know, we spend a massive amount of time on this show talking about the output of the human machine.
We do. We're always looking at the results, aren't we?
Exactly. We talk about psychology, we talk about habits, productivity hacks, social dynamics, all of it. But today, we're going to do something fundamentally different. We are going to strip the paint off the walls.
Lift up the floorboards.
And look at the wiring.
We are conducting a structural survey of the engine room itself.
Precisely. We are looking at the architecture of thought.
Okay.
And I don't use that word architecture lightly. We have a stack of sources today that move us well past the pop psychology notions of, left brain versus right brain.
Oh, absolutely. We're getting into the actual physical infrastructure.
The infrastructure that dictates everything from a simple toe wiggle to the most profound moment of creative genius. We are looking at the wetware.
It's a fascinating landscape to traverse, and you're quite right to emphasize the physical nature of it. When we look at the sources for this deep dive, and we're talking about everything from, granular neurobiology texts from Johns Hopkins and the Mayo Clinic, all the way to cutting-edge research on flow states.
From places like Frontiers and Behavioral Neuroscience.
Yes. And what emerges from all of this is a picture of a biological machine that is, well, it's defined by a very specific, and I'd say very precarious, tension.
It's not just a lump of gray jelly, it's a polarized environment.
It is. The central theme here, the hook, if you will, is what the literature refers to as the neurobiological dialectic.
Now that sounds incredibly highbrow and academic.
It does, but it's actually quite simple. It's about how the brain manages to be two contradictory things at once. On the one hand, it's a collection of specialists, distinct parts doing very distinct jobs.
That's the functional segregation part.
Exactly. But at the same time, it has to be a unified, integrated team. That's the functional integration.
And the reason we're doing this deep dive is because understanding that tension explains us, doesn't it? It explains why we can focus, why we get distracted.
And how we achieve those rare moments of brilliance.
We're going to trace that arc all the way up. We're starting with the microscopic voltage changes in a single cell. The hardware, really, and we're going to end up explaining how a jazz musician improvises a solo.
Or how a mathematician cracks an impossible proof. It's the journey from the neuron to the flow state.
But before we get to the poetry of high performance, we have to respect the machinery. We have to look at the primary regulator for the entirety of the human experience, as one of our texts calls it.
And the scale is it's mind-boggling.
It is almost impossible to conceptualize.
It really is. We are talking about approximately 86 billion neurons. Now, that number gets thrown around a lot, but just stop and think about it for a second. 86 billion.
It's a galaxy.
It is. And for every single one of those neurons, there's roughly an equivalent number of glial cells supporting them. It's an entire universe inside the skull.
And yet, despite that complexity, despite the billions and billions of connections, there is a fundamental unit of currency, isn't there?
Yeah.
There is a single mechanism that makes all of thought possible. We need to talk about the spark.
We do. To understand thought, you have to understand the neuron. And structurally, it's a It's quite an elegant device. You've got the cell body, the soma, which is the command center.
Okay.
Then branching out from that, you have the dendrites. You can think of those as the receivers, the antenna gathering information from all its neighbors.
And then the axon is the transmitter.
The transmitter, yes. The long cable that sends the signal out.
But the magic isn't in the shape, it's in the electricity.
Yeah.
I think for a lot of people, the idea of brain waves or electrical signals is a bit abstract. It sounds a bit like, well, like magic.
It does. But our sources on neuronal transmission break this down into a very, very precise electrochemical event. It's not magic at all, it's physics.
Pure physics.
Absolutely. And it all operates on a principle of tension. When a neuron is at rest, it isn't truly resting in the sense of doing nothing. It's actively holding a charge. It's like a drawn bowstring or a dam holding back a river of water. We call this the resting potential.
So it's actively waiting.
It is working very, very hard to wait. The inside of the cell is negatively charged relative to the outside, sitting at about minus 70 millivolts.
Okay.
And it maintains this tension by constantly actively pumping ions in and out. It's kicking sodium out and pulling potassium in. It's a tiny biological battery, fully charged and ready to go.
It's waiting for a trigger. And this is where we get into the action potential. This is the fundamental unit of communication in the whole nervous system.
The bit, the 0 or 1 of thought.
Exactly. So if the neuron receives enough stimulation from its dendrites, enough yes votes, if you will, to raise that voltage from minus 70 up to a specific threshold.
Which is usually around minus 55 millivolts.
Right. At that point, the dam breaks.
And dam break is absolutely the correct metaphor. This isn't a gentle leak. This is what we call the all or nothing event.
There is no such thing as a half fire, is there? You can't have a small thought or a big thought at the level of a single neuron.
No. It's completely binary. It's digital, 0 or 1. Once you hit that minus 55 millivolt threshold, these things called voltage-gated sodium channels just snap open.
And sodium has been desperate to get in.
Desperate. It's positively charged, and it's been held outside in this high concentration, so it floods the cell. The voltage just rockets up to plus 40 millivolts in a fraction of a millisecond. That is the spark. That is the signal.
But what I found fascinating in the reading, and what I think is often missed in the high school biology version of this, is what happens immediately after. The brain can't just leave the switch on. It has to reset.
It must. If it stayed at plus 40 millivolts, the neuron would be completely useless for any future signal. It needs to repolarize.
So it has to get back to that waiting state.
It has to. So the sodium channels slam shut, and then another set, the potassium channels open up. Potassium rushes out, taking its positive charge with it, and that drops the voltage back down. But, and this is a really crucial detail for understanding how our brains process information, it actually overshoots.
It goes too far.
It does. It goes too negative for a moment, into a state we call hyperpolarization. And this creates what we call the refractory period.
I want to pause on this because the text suggests this is actually a physiological limit on human intelligence, or at least our processing speed.
It is the absolute speed limit of the mind. During what we call the absolute refractory period, that neuron cannot fire again. It doesn't matter how exciting the news is. It doesn't matter if you're in mortal danger.
It's offline.
It is physically offline. The physics of the ion channels dictates it. It needs that millisecond or two to reset the gradients.
So we cannot fire infinitely fast. There is a hard physiological cap on our processing speed imposed by the chemistry of the cell membrane itself.
Precisely. We are biological entities, not silicon chips. We have reset times.
And speaking of speed, that brings us to another piece of the hardware that I think is often overlooked. We talk about gray matter a lot, but we really need to talk about white matter. We need to talk about myelin.
Ah, myelin, the unsung hero of high-speed cognition. If you look at an axon, that wire carrying the signal, it can be either bare or it can be wrapped in this fatty substance called myelin.
And that's produced by certain cells.
Yes, cells called oligodendrocytes in the central nervous system.
I love the analogy one of the texts used, comparing it to the insulation on an electrical cord. But it's not just to stop the signal from leaking out, is it? It's more clever than that.
Oh, much more clever. It allows for something called saltatory conduction.
Which sounds like a dance move.
It does. It comes from the Latin saltare, which means to jump.
Ah, okay.
In an unmyelinated nerve, that electrical spark we just described has to travel step by step down the entire length of the axon. It's like a wave moving through a stadium crowd. It has to go person by person. It takes time.
It's slow.
It's relatively slow, but with myelin, the signal can jump. The insulation has these little gaps in it called the nodes of Ranvier, and the electrical signal just leaps from one node to the next.
And the difference in speed is, it's not trivial, is it? We aren't talking about a 10% boost.
No, we are talking about orders of magnitude. An unmyelinated signal moves at maybe 0.5 to 2 meters per second. A myelinated signal can travel at up to 100 meters per second.
Wow. And to put that in perspective, the text gave a great example regarding pain.
Yes, the stubbed toe example. If you didn't have myelination on the nerves from your foot and you stubbed your toe, the signal would travel so slowly that you wouldn't feel the pain for about 4 seconds.
4 seconds. You'd look down, so you'd kick the table and then just have to wait for it.
You'd wait, and then ouch. With myelin, the feedback is almost instantaneous. It allows us to exist and react in real time.
So we have the electrical signal rushing down the axon at 100 meters per second. It hits the end of the line, but now it has to cross the gap to the next neuron. And this is where it switches from electricity to chemistry. This is the synapse.
The synaptic cleft. This is where the story changes completely. The electrical charge, the action potential, hits the terminal button at the end of the axon.
Right.
And it triggers the opening of a new set of channels. Voltage-gated calcium channels. Calcium rushes in, and it binds to a protein with a fantastic name.
Go on.
It's called synaptotagmin.
I have to say, synaptotagmin is a great word. It sounds like a villain in a sci-fi movie.
It's a critical protein, though. It acts as the calcium sensor. When it detects that influx of calcium, it triggers these little bubbles, these synaptic vesicles filled with neurotransmitters.
The chemical messengers.
The messengers, exactly. It tells them to fuse with the cell membrane and dump their cargo into that tiny gap between the neurons.
And this is where the message gets refined, isn't it? Because not all chemical messengers are saying the same thing. It's not just a simple pass it on.
Correct. And this is where the incredible complexity of thought truly arises. You essentially have a gas pedal and a brake pedal at every single connection.
Okay, so what's the gas?
The primary gas pedal, the main excitatory neurotransmitter, is glutamate. Its job is to tell the next neuron, fire, pass this message on. It binds to receptors on the other side, like AMPA and NMDA receptors, which lets positive ions in, pushing that next cell closer to its minus 55 millivolt threshold.
And the brake.
The brake is GABA, gamma-aminobutyric acid. It's the primary inhibitory neurotransmitter. It does the opposite. It tells the next neuron, don't fire, stay quiet.
How does it do that?
It usually works by letting negative ions, like chloride, into the cell. This makes the inside of the cell even more negative, moving it further away from that firing threshold.
So every single thought we have, every decision, every flicker of an idea is essentially a democratic vote happening at thousands of synapses simultaneously.
That is a beautiful way to put it. It is a constant, dynamic process of summation. A single neuron might have thousands of connections. Some are screaming fire with glutamate. Others are whispering hush with GABA.
And it's just doing the math.
It does the math. It sums all these inputs across space and time. If the eyes have it, if the excitatory signals win out and the threshold is reached, a new action potential fires and the thought continues down the line. If the nays win, the signal dies right there.
It really creates a picture of the brain not as a static computer, but as this seething dynamic storm of chemical negotiation.
And that negotiation is the foundation of everything. But to understand how that storm becomes a personality or a memory or a skill, we have to zoom out. We have to look at the macroarchitecture because these neurons aren't just thrown into a pile. They are organized into highly specialized structures and regions.
Okay, so this brings us to part 2 of our deep dive. The macroarchitecture, or as the sources say, functional segregation. We often hear about the lizard brain versus the monkey brain, but the sources we have today are asking us to be a bit more precise than that. Let's start from the bottom up.
At the very base, you have the switchboard and the foundational systems, the brainstem. This is the oldest part of our brain, evolutionarily speaking.
The real lizard brain.
If you want to use that term, yes. It handles the absolute non-negotiables. Breathing, heart rate, sleep cycles, consciousness itself. It's the foundation of survival.
And sitting right behind it is the cerebellum. Now, I grew up learning that the cerebellum was for balance and motor control. If you can ride a bike, thank your cerebellum. But the new research in our stack suggests it does a lot more than just that.
This is a major shift in neuroscience. For decades, we thought the cerebellum was purely motor control coordination, posture, fine-tuning movement. But we now see that it has extensive connections to the thinking parts of the brain, the prefrontal cortex.
So what's it doing there?
Well, it appears to regulate cognitive fluidity in the same way it regulates physical fluidity.
Cognitive fluidity, what does that actually look like in practice?
Well, think about a clumsy physical movement. It's jerky, uncoordinated, poorly timed. Now think about a clumsy thought.
Okay.
Social awkwardness, or an inability to smoothly sequence a logical argument, or emotional outbursts that don't quite fit the situation. The research suggests the cerebellum helps smooth out our thoughts and even our emotional rhythms, providing the timing and sequencing.
So a clumsy cerebellum might lead to clumsy thoughts. That's fascinating.
In a manner of speaking, yes. Moving up slightly from there, we hit the thalamus. If the brain is a major corporation, the thalamus is the central mailroom or the executive switchboard.
All the information goes through it.
Almost every piece of sensory information, sight, sound, touch, taste, it all goes to the thalamus first. And the thalamus acts as a gatekeeper, deciding where to route that information in the higher brain centers.
And then we get to the real celebrity of the brain structure world.
Yeah.
The limbic system, the emotional center.
The seat of passion and memory. Here you have, first and foremost, the amygdala, that little almond-shaped structure.
This is the fear center, right?
It's often called that, but it's a bit more than just fear. It's the threat and reward detection system. It processes fear, aggression, but also pleasure. Its main job is to tag experiences with emotional significance. It says, pay attention, this is dangerous, or this is wonderful.
And right next to it, literally adjacent, is the hippocampus.
The seahorse, yes, named for its shape. And it is absolutely crucial for memory formation, specifically for converting our short-term experiences into lasting, long-term memories.
And it's no accident they're neighbors, is it?
Not at all. It's a brilliant piece of architecture. The amygdala and the hippocampus sit right next to each other and they talk constantly. That is why emotional memories are so incredibly potent.
Which explains why you can remember exactly where you were during a traumatic event or a fantastically happy one, but you can't remember what you had for lunch last Tuesday.
Exactly. The amygdala essentially stamps the memory with a priority label. It tells the hippocampus, this one matters, burn this one into the archives. The lunch on Tuesday had no emotional tag, so the hippocampus just lets it go.
And then finally we reach the top floor, the cerebrum, the cerebral cortex. This is what really makes us human.
This is the great wrinkled thinking center. It's divided into the 4 great lobes. You have the occipital lobe at the very back, which is almost entirely dedicated to processing vision.
Right.
You have the temporal lobes on the sides, handling language comprehension, hearing, and memory.
Yeah.
The parietal lobe on top, dealing with spatial awareness, touch, navigation.
And the crown jewel, the frontal lobe, right behind your forehead.
The CEO of the brain. Decision-making, impulse control, personality, planning for the future. It's the seat of our highest cognitive functions.
And connecting the 2 hemispheres of this massive structure is the corpus callosum.
The Great Bridge. It's a huge bundle of myelinated white matter fibers that allows the left and right hemispheres to communicate in real time. Without it, you essentially have 2 independent brains trying to operate one body.
So we've got these distinct parts. We have the hardware and the macroarchitecture. But here's where the story really shifts, isn't it? Our sources suggest that looking at the brain as a collection of separate organs, this is the fear spot, this is the math spot, is outdated. It's too simplistic.
It is. That way of thinking is giving way to what we call network neuroscience.
Right.
We used to map the brain like a phrenologist, looking for bumps for different functions. Now we map it like a traffic engineer. We look for the highways, the hubs, the patterns of communication. And it turns out there are 3 major large-scale networks that dominate our cognitive lives.
Let's unpack these, because understanding this trio really changed how I view my own focus and, well, my own daydreaming. The first one is the default mode network, the DMN. And honestly, it has a bit of a reputation problem in the productivity world.
It does, yes. The default mode network was discovered almost by accident. Researchers noticed that when people were lying in an MRI scanner and told to do nothing, just rest, their brains were incredibly active.
They weren't off.
Not at all. They were blazing with activity in a very specific set of regions: the medial prefrontal cortex, the posterior cingulate cortex, and others.
So this is the daydreaming network.
That's how it was initially framed, yes.
Yeah.
It's the network that comes online when you aren't focused on a task in the outside world. It handles self-referential thought thinking about yourself. It handles autobiographical memory, thinking about your past, imagining your future. It's mental time travel. It's the me network.
And usually when we need to get things done, we have to shut that guy up. We have to switch to the second major network,
The Executive Control Network, or ECN. The boss. Exactly. It's anchored in regions like the dorsolateral prefrontal cortex. This is the network for goal-directed behavior. Working memory, logic, complex problem solving, focusing your attention on the external world. When you are solving a math problem or writing a report or navigating heavy traffic, the ECN is in charge.
And the relationship between the DMN, the daydreamer, and the ECN, the executive. It's usually antagonistic, right? They don't typically play well together.
Historically, that's what we've seen. We call them anti-correlated. They work like a seesaw. When the executive network goes up to focus on a task, the default mode network normally goes down. You have to stop thinking about yourself in your daydreams so you can think about the problem at hand.
If it doesn't shut down.
That's when you get distracted. If the DMN stays active while you're trying to work, you make mistakes, your mind wanders, you start wondering what you're going to have for dinner instead of focusing on the spreadsheet.
But there's a third player here, the switch. Because we don't just randomly flop between the two. Something has to direct the traffic.
Indeed. There's a mediator, the salience network. This one is anchored in the anterior insula and the anterior cingulate cortex. Its job is to constantly scan the environment, both your internal state and the external world, and decide what is important, what is salient.
So it's the arbiter of attention.
It is the ultimate arbiter. If it detects a sudden loud noise or a pain in your side or a crucial piece of information on a screen, it's the salience network that says, whoa, this is important, and it toggles the switch.
It shuts down the DMN and fires up the ECN to deal with it.
Precisely. Or if you get bored with the task and nothing important is happening, it might say, all right, let's let the DMN take over for a while.
So in a typical brain state, we have this constant toggling. Daydreaming.switch. Focus.switch. Daydreaming, that's the normal rhythm of our minds.
That is the standard operating procedure for most of our waking life.
But, and here's where it gets really, really interesting. Our deep dive into the research on flow and creativity suggests that this seesaw rule isn't absolute. In fact, the most extraordinary human experiences seem to happen when that rule is broken.
This is the most compelling part of the new research, I think. We are moving into part 4. Flow and creativity. We've defined the networks, but now we get to see what happens when they do something completely unexpected.
Let's start with flow. We have to mention Mihaly Csikszentmihalyi's famous concept, being in the zone.
A state of complete immersion in an activity. You have this energized focus, a full involvement, and you enjoy the process. You lose your sense of self-consciousness. Time dilates.
And it happens under a very specific condition.
Yes. It happens when the challenge of a task is perfectly balanced with your skill level. If the challenge is too high for your skills, you get anxiety. If your skills far exceed the challenge, you get bored. But right in that channel in the middle, that's where you find flow.
Now, for a long time, the prevailing neuroscientific theory was that flow was a state of transient hypofrontality. Basically, the prefrontal cortex, the CEO, just shut down.
It went to lunch.
It went to lunch. And the more automatic, skilled parts of the brain took over.
That was the theory proposed by Arne Dietrich and others. And it makes a certain intuitive sense, doesn't it? You lose your sense of self, so the self part of the brain, the prefrontal cortex, must be off. You stop overthinking, so the thinking part must be off. It sounds logical.
But the new evidence, specifically the review by Barnett and Vasu, and the work by researchers like Roger Beatty, says not so fast.
Exactly. The modern imaging data shows it's much more sophisticated than that. It is not just a shutdown, it is a fundamental reorganization. It's a state of highly optimized network dynamics. And the big headline here is what they call the paradox of coupling.
This blew my mind. During flow, and specifically during tasks that require creative improvisation, the default mode network and the executive control network, the two mortal enemies, start working together.
They synchronize. It's a direct violation of the normal protocol. In these highly creative states, you see the DMN, the daydreaming network, generating spontaneous associations, wild ideas, distant memories, loose connections from the attic of the mind. But simultaneously, the executive control network is online, not to suppress those ideas, but to evaluate them, direct them, and integrate them into the goal-directed task.
So instead of the CEO shutting the door on the daydreamer, the CEO is inviting the daydreamer into the boardroom and saying, right, give me everything you've got and I'll figure out how to use it.
That is a perfect analogy. The Beatty study on divergent thinking is particularly illuminating here. They put people in scanners and asked them to do the alternate uses task, come up with creative uses for everyday objects like a brick.
Right, it's a paperweight, it's a doorstop, it's a weapon, it's a source of red dust for a painting. It's a tiny tombstone for a hamster.
Exactly. And what they saw was this beautiful dynamic connectivity. In the early phase of idea generation, the brain strongly couples the DMN with the salience network. It's searching for ideas, rummaging through that attic of the mind to see what's interesting.
Okay, so it's the search party.
It's the search party. But in the later phase, as the ideas get more complex and need to be refined, the DMN couples with the executive network to select, elaborate on, and polish the best ones.
So creativity isn't just uninhibited right brain chaos, it's controlled chaos.
Controlled chaos is the perfect operational definition of high creativity. It is the superior ability to exert top-down control from the ECN over spontaneous bottom-up thought from the DMN. It's high-efficiency information transfer between regions that usually ignore each other.
It's the jazz musician who knows the scales and music theory perfectly,
That's the executive network.
but is allowing their fingers to drift into the unknown to find a new melody.
And that's the default mode network. The two are in perfect conversation.
There's another piece of the flow puzzle that connects back to the limbic system, the emotional regulation. Because a key feature of being in flow is that you aren't worried. You aren't self-conscious.
This is absolutely critical. In a true flow state, we see a distinct downregulation, a quieting of the amygdala. The fear and threat detection center goes offline.
Which would explain why extreme athletes can do terrifying things in a flow state without panicking. The inner critic is gone.
The panic signal is muted. The brain essentially says, I have the skills to handle this challenge, so I don't need the alarm bells ringing. And simultaneously, we see distinct connectivity patterns between the executive regions and the nucleus accumbens.
The reward system.
The reward system. The brain is releasing its own dopamine, reinforcing the behavior, making it feel good. So you have this incredible state of high focus, high creativity, zero fear, and immense intrinsic reward.
It really does sound like a superpower.
In many ways, it is the optimal state of human functioning. It is the brain firing on all cylinders with the brakes cut on fear and self-doubt.
So if this is the optimal state, the obvious next question is, how do we get more of it? How do we apply this understanding of the brain's architecture to our actual everyday lives? This brings us to part 5, the neuroscience of productivity.
And the first step is to stop treating the brain like a computer that can run continuously until the battery dies. It is a biological organ with biological rhythms. It has hard limits, just like that neuron has a refractory period.
One of the key concepts from the sources here is the ultradian rhythm. We all know about circadian rhythms, the 24-hour sleep-wake cycle. But ultradian rhythms are the shorter cycles within the day.
They are the 90 to 120-minute cycles of alertness and focus. Your brain can maintain high-frequency beta wave activity, which is what you need for intense focus, for about 90 minutes. After that, it needs to trough. It needs a reset.
And this isn't a suggestion, is it? It's a metabolic reality.
It's a metabolic reality. Those sodium-potassium pumps we talked about at the very beginning, they run on energy. The neurotransmitters in the synapse need to be replenished. The brain is a physical system that builds up waste products.
But what do we usually do? We feel that dip and we grab a coffee and push through.
And that is a fundamental physiological error. When you push past that 90-minute peak without a proper break, you deplete the very neurochemicals required for executive function. You enter a state of decision fatigue. The prefrontal cortex gets tired and goes offline.
And the limbic system takes over.
The emotional, reactive, short-sighted brain starts to take over. That is when you get irritable. That's when you get distracted easily. That's when you send the email you immediately regret.
Because you're operating on fumes and your fight or flight system is driving the car.
That's it, exactly.
So the strategy here is focus blocks. Work intensely for 90 minutes, then take a real break. But the nature of the break matters, doesn't it?
Yeah.
You can't just switch from a spreadsheet to scrolling social media.
Absolutely not. A real break is one that actually disengages the executive and salience networks. Scrolling your phone just demands more attention. A real break is letting the DMN take over. Go for a walk, stare out a window, listen to some music, let the system flush. There's even a system called the glymphatic system that clears out metabolic waste from the brain, and it works best during these rest periods.
Another big productivity myth the sources absolutely destroy is multitasking. I feel like we all know on some level that multitasking is bad, but we all do it anyway.
We do, but neuroscience is unequivocal on this point. The human brain cannot multitask in the sense of doing two cognitively demanding tasks at once. It's a biological impossibility.
So what are we doing?
We're task switching. We are toggling our attention back and forth very, very rapidly.
But there is a cost to that toggle. It's not a free action.
A huge cost. It's called the switching cost. Every single time you switch from writing an email to checking a text message and then back to the email, you are burning precious glucose and oxygen just to reorient the neural context. You have to load the email program back into your working memory.
And the efficiency loss is staggering.
Research suggests this can lead to up to a 40% loss in overall efficiency. You are literally making yourself 40% stupider by trying to do two things at once.
That is a terrifying statistic, 40%.
It also creates what's called attention residue. When you switch tasks, part of your brain is still stuck thinking about the previous task. You never get your full cognitive bandwidth on the current one. The architecture demands single tasking for high performance.
Let's talk about stress. We mentioned the amygdala earlier, the alarm system. What happens to the brain's architecture under conditions of chronic stress?
It gets remodeled, and not in a good way. Chronic stress floods the system with the hormone cortisol. In short bursts, cortisol is useful, but in high sustained doses, it's actually neurotoxic.
What does it do?
It physically shrinks the hippocampus. It kills brain cells in your memory and learning center. And conversely, it strengthens and grows the amygdala. It builds a bigger, more sensitive alarm system.
So you become literally wired for anxiety.
You physically rewire your brain to be more fearful, more reactive, and less capable of complex, long-term thought. This is why neuroplasticity is a double-edged sword. We often hear about it as this wonderful thing, I can learn French. But you can also plastically wire yourself for burnout and anxiety.
But the reverse is also true, isn't it? We can use that plasticity to wire ourselves for success. Gamification was mentioned in the sources.
Yes. This is about consciously using the dopamine reward system to our advantage. The brain loves to see progress. It loves feedback loops. So breaking a big, intimidating project into tiny micro goals.
Like write one paragraph instead of write the whole report.
Exactly. Each time you tick off a micro goal, you get a little dopamine spike. I did this, I finished that. That little reward keeps the executive network fueled and motivated. It prevents the limbic system from getting overwhelmed and giving up.
And finally, environment. We are biological creatures. Yet we so often stick ourselves in gray, fluorescent-lit boxes for 8 hours a day.
And the brain is simply not designed for the cubicle. The sources discuss the importance of biophilic design. Just having plants in your line of sight or access to natural light can help regulate your circadian rhythm and measurably lowers cortisol.
And big companies are catching on to this.
Companies like Google and Zappos are using these principles. They aren't putting plants and nap pods in the office just to be trendy. They are doing it because the science shows that a relaxed, well-rested brain is a smarter, more creative, and more productive brain.
It seems like the common thread running through all of this, from the neuron to the office design, is respect. Respecting the physiological infrastructure.
That is the ultimate takeaway. You wouldn't drive a Formula One car in first gear for 500 miles and expect the engine to last. Yet we treat our brains with almost zero regard for their biological operating manual. We interrupt them constantly, we starve them of proper rest, we flood them with stress hormones, and then we wonder why we can't focus or come up with good ideas.
So let's bring it all home. We have traveled from the sodium ion rushing through a tiny channel in a cell membrane,
All the way up to the massive, sprawling networks of the DMN and ECN.
to the flow state of a jazz musician improvising a solo.
It is a remarkable journey. We start with a simple binary spark on or off. That binary code builds into localized processors, the lobes and nuclei doing their specific jobs. Those processors then link up into vast, often competing networks, our capacity for deep focus versus our tendency to daydream.
And in our highest moments, those competitors shake hands and synchronize.
They do, and that synchronization is what we experience as genius, as flow, as effortless creativity. It is the harmonious integration of the entire machine.
I want to leave our listeners with the thought that kept nagging me as I was going through these sources. We talked about how flow is this almost magical state where these opposing networks cooperate. And we talked about neuroplasticity, the fact that the brain changes and rewires itself based on what we do repeatedly.
I see where you're going with this.
If flow is a distinct, measurable neural state, and if our brains are plastic, then can we train ourselves to live in flow?
That is the provocative question, isn't it? If we stop treating flow as a happy accident that sometimes happens and start treating it as a trainable skill like learning to play the piano or speak a language, could we, through practice, actually strengthen the connections between the DMN and the ECN?
Could we lower the threshold for them to couple?
Could we eventually stabilize that network coupling? Could we create a brain that is permanently, or at least more readily, in the zone, a state where the ego is quieted, the fear is gone, and creativity is the default setting, not the exception.
A natural antidepressant and performance enhancer built right into our own wiring.
It is, at least in theory, a possibility. And it might just be the next frontier of human evolution. Not changing our biology, but finally mastering the software to run it at its absolute peak efficiency.
Something to mull over the next time you're trying to push past that 90-minute focus block.
Indeed. Respect the architecture.
Thanks for diving deep with us. We'll catch you on the next one.